Welcome to the Explainer. Have you ever been staring at a differential equation and just thought, wait a second, why is having an e to the x on one side so much easier to handle than a simple x squared? Well, today, we are cracking that exact code. We're going to dive deep into the particular integral and figure out why that is. Let's do it. Okay, so this is the heart of the matter, right? Why are there these two totally different paths? You've got an exponential function and you've got a polynomial. On the surface, they both seem pretty straightforward. But, and this is the key, when you're trying to find that particular solution, it's like you need two completely different sets of tools. And that's the big puzzle we're going to piece together today. So here's how we're going to tackle this. First, we'll lay out the puzzle itself. Then, we'll take what I call the direct route for exponentials, followed by the more winding path for polynomials. We'll put them side by side to really see the difference, and then we'll look at what happens when the rules suddenly seem to break. Right, Section 1, the PI puzzle. Before we can even talk about the different methods, we gotta get on the same page about what this particular integral thing even is, and, more importantly, why we should care about it. Okay, so here's the big idea. You see that function on the right-hand side of the equation? Think of that as an input or a forcing function. The particular integral, which we call yp, is the part of our answer that is tailor-made to respond to that specific input. It's the particular solution just for that function. And this is so important to remember. Your final answer is never just the particular integral. Think of it like two puzzle pieces that have to click together perfectly. You've got the complementary function, the yc, that's kind of like the system's natural default state. And then you add our particular integral, the yp, which is the response to that specific thing you're hitting it with. You absolutely need both to get the full picture. All right, let's hit our first path. We're going to tackle those exponential terms, and you're about to see why I call this the direct route. Honestly, it feels a little bit like a magic trick. And here it is, the golden rule. It's almost unbelievably simple. You just take the constant a out of the exponent, and you literally just plug it in wherever you see the differential operator d. Now, the reason this works is because of the beautiful nature of the exponential function. When you differentiate e to the ax, what do you get? You always get a multiple of e to the ax back. The function's basic shape never changes, and that's what unlocks this amazing algebraic shortcut. So it really boils down to the simple three-step dance. First, you spot the a. Second, you swap out all the d's for that a. And third, you just do the arithmetic. That's it. As long as that calculation doesn't make you divide by zero, but we'll get to that little problem later on. Let's see this in action with a real example. So here, the function on the right side is 3 times e to the power of x over 2. That means our constant, our a, is just 1/2. Simple enough. And boom, look at that result. So we take our a of 1/2 and we plug it into the operator on the left. D cubed becomes 1/2 cubed, that's 1/8. Minus 2d becomes minus 2 times 1/2, which is just minus 1. Then we have a plus 1. So 1/8 minus 1 plus 1, the whole operator just turns into the number 1/8. Our pi is just the original function divided by that number, and bam, 24 times e to the x over 2. So fast. Okay, time to switch gears completely. If the exponential method was a straight, freshly paved highway, well, the polynomial method is more like a winding country road. It'll get you where you're going, but, you gotta take your time and navigate the turns. And here's why the path is so different. Think about it. When you differentiate a polynomial like x squared, its whole form changes. It becomes 2x, then it becomes 2, and then it becomes 0. There's no convenient constant a that we can just plug in. We have to respect d for what it actually is, an instruction to differentiate. And that means we need a totally different strategy. So yeah, this process, it definitely looks more involved, because it is. The whole idea here is that you can't just apply that fractional operator in one go. Instead, we use this really clever algebraic move, usually a binomial expansion, to rewrite that fraction as a long, potentially infinite, series of d and d squared and d cubed. It essentially turns one big, impossible operation into a bunch of smaller, manageable steps. Let's make this real with another example. This time, our input on the right is just a simple x squared. No substitution allowed. We have to take that winding path. Okay, so after a bit of algebraic wrestling, which usually means factoring out the lowest power of d and then using a series expansion, that complicated fractional operator gets magically transformed into the series you see here. Now, I know it looks a little scary, but look closer. It's just a constant, then a d term telling you to differentiate once, then a d squared term telling you to differentiate twice, and so on. We've turned a division problem into a sequence of differentiations. And this is where the magic happens. We take that expanded operator and apply it to x squared piece by piece. That 1 over d term from our factoring, that's an integration, turning x squared into x cubed over 3. Then the constant multiplies it, the d term hits it and gives us 2x, the d squared term hits it and gives us 2. We gather up all these pieces, do the math, and they combine to create a brand new polynomial. And that polynomial, that is our particular integral. Whew! Okay, so we've driven down the direct highway and we've navigated the winding road. Now let's park them side by side and really nail down what makes these two methods so different. I mean, this slide just lays it all out, doesn't it? For exponentials, the method is substitution. It's an algebraic trick. For polynomials, the method is operator expansion. It's a procedural application of calculus. One is basically just algebra. The other needs tools like binomial series and actual differentiation. We're talking two completely different mindsets for two different kinds of functions.
All right, but let's go back to that problem I mentioned. What happens when our super easy direct route for exponentials suddenly hits a dead end? What if that substitution makes you try to divide by 0?
And here it is, the classic failure case. Our a here is -1, but look what happens when we plug -1 into the operator. We get 0 in the denominator. The whole method breaks down. Now, what this is really telling us is something deeper. Our input function, e to the minus x, is already part of the system's natural behavior. It's in the complementary solution, so our standard approach just isn't going to cut it. But don't worry, there's a really elegant fix for this. The solution has two parts. First, we multiply our usual guess by x. That kind of bumps it up a level, so it's not duplicating the complementary function anymore. And second, instead of the original operator in the denominator, we use its derivative. It's a very specific, very precise tweak for this exact problem. So, after all that, what's the real lesson here? It's that the function on the right-hand side is everything. It's not just a minor detail, it is the blueprint that dictates your entire strategy. We've seen the unique paths for exponentials and polynomials, which of course leads us to a bigger question. What about other functions? What about sines and cosines? Or maybe a mix of a polynomial times and an exponential? Well, you guessed it, each one of those might just require its own unique path. And understanding why is the real key to cracking the code.